Okay, so welcome to the second lecture in neural networks and deep learning. Maybe you see a bit of a surprising title today, which is called Hardware and Software, and you might think, what is this? Why are we talking about this? The motivation is a bit that if you look at what current neural networks are, of course, you on the one hand try to build the best, well, that's the main goal, to build somehow a model which gives you the best performance. But you cannot do that like in your wished world. But for example, you want to build it that you can train big models, because we know that the larger your more models you can train, and the bigger the model is, normally it's getting better. So when you're thinking about new architectures, it's also good to think about on what architectures do I want to run it, so that you maybe can use that originally during your development. And that's why exactly what we're doing today is we look, okay, in which environment are we building these deep learning algorithms? And of course, there are two important parts of this environment where you build your deep learning models. On the one hand, it's the hardware on what it should run. And on the other hand is, of course, also the software, and it's good to know about it a bit. And I guess you experience a bit. Of course, you prefer to run things on software which is easy to use and so on. And there has been large advancements. What we will look today. Last time you maybe struggled a bit with all the derivations you have to build and like implement your backpropagation. And 15 years ago or something, you would have to do that for all your models you're developing. The nice thing now is you don't have to care anymore about it. Computers can do it better. And we'll see that typically nowadays, if you implement some new architecture, you can use automatic derivation. And therefore, we'll try to have a bit on a look on this today, so that we then can further look in the next weeks on the different architectures. And you should keep this in mind a bit, because that partly motivates us. And we'll see, especially nowadays, like if you look at attention or something like that, what we cover, they develop dedicated algorithms that fit very well the architecture, so the hardware architecture. So to do that, what we will do today is we'll start a bit with a motivation on why we think this is helpful or good. And then we will look into what do we really need to do in neural networks. So what is the typical like computations you have? We'll especially look again at the matrix formulation, which we saw a bit before, because this is essential. If you look at the implementation of neural networks from this matrix multiplication perspective, you directly see that they are very well fit into GPUs. We'll look how you implement things on GPUs. Then we'll have a bit of further look on, yeah, now you can do fast in one GPU, but as a developer, you're never happy with your hardware, and you want to have more power and process more data and build bigger models. And then the easiest way to do it is to run it not on one GPU, but you run it on 2, 3, 5, and more GPUs. And then you're running it not on one node, but on many nodes and so on. So we'll look briefly on what algorithms you can do there. And then the last part, we'll go to the software part, where now the idea is that, okay, if I always have to implement like exactly how to calculate the backpropagation, we've done that for the simple case. It's possible. It's also, of course, possible for the more difficult networks, but maybe it's not really convenient. It's not what you want to spend maybe most of your days on. So we'll see how that is nowadays done with some type of automatic derivation, where you mainly only have to implement your forward pass and the rest is done for you. So let's start with why we think this is, or why you should care about that, and what is the motivation behind it. If you want to do one important thing nowadays by developing neural networks and deep learning, it's going fast. You also want to be fast. If you have an idea, maybe somewhere in the world, somebody similar has a similar idea. And so you have to be somehow fast in like having your idea. So it's in the end your idea. And you don't want to always reinvent the wheel. So the question is, can you reuse some things? And so the question is, can you make things easier? And how you can do that, or what is there important, is, as I said, on the one end, for the hardware, it's really important that you can train on large data, and therefore that you can only do if you do fast training. And of course, later you also maybe want to have fast inference. I mean, of course, maybe for you, if you're a researcher, you're more interested in the training, then you test it and you can write your thesis and you're done. But if you're now looking at this more from a application perspective, when you're working at a company, it might be different. There you once train your model, and then you want a lot of customers to pay for using the model. So most of the computation is then more on the inference and no longer in the training. So both is important, and therefore it makes sense to look how to do that. And for software, as I said, you want to have something where you can fast develop new ideas and you don't have to re-implement a lot of things over and over again. However, this of course is not only you're not only like acquiring, oh, I want to have this best and then this is all, but there is a bidirectional infrastructure influence. So the thing is, if you have a good infrastructure, that also leads that I can fast try a lot of different ideas. I can do more, but also it leads to a bias. So it might be that two models or two architectures are similarly good. However, if the one is better supported by your hardware, you can train it on larger models and it just will give you better performance than the other one. Might be for the same data, for the same data, they would perform the similar, but if the one needs 1 week to train and the other needs 1 year to train, then you'll go for the one which uses 1 week to train. And therefore, it's nowadays often that you're not just developing your new architectures just out of nowhere and like think about what is good for purely predicting, but you also look what is supported by the current hardware. How can I implement this fast? Because only if that's possible, you can build these like huge networks we're having. I mean, a lot of the things nowadays, by scaling up things, there's a lot of engineering around it. And you might even use some type of architecture which is not as good or not as exact, but if you can then train on 10 times as much data, normally it will lead into better performance. What does that mean? So for what we will be looking at here, it's mainly like the two parts today, as I said. So for hardware, I mean, at the moment, at least, GPU is a thing which is running your deep learning based models. If you want to train a neural network, you need a GPU, to be honest. Otherwise, it's like small toy project, but you can't do the computation on anything else. You see that there's nowadays large data centers which order like huge amounts of GPUs. They're normally out of stock directly, and everybody wants to have as many GPUs as. Therefore, it's good to know a bit about what is special about them, how to program them. Of course, you might be lucky by now, so there's a good abstraction level. You can implement your algorithms without knowing all the details, but some basic understanding is normally good in order to develop, as I said, algorithms that really work well on that. And for the software side, it's good to know that this like automatic derivation is existing because again, it makes things for you normally a lot easier. So yeah, this is a bit like the motivation why we put this lecture here today and where we introduce these two a bit in advance to all the others. So when we're now developing or looking at architectures, we can always think about and we have the background in order to build upon that. So let's, as another one, let's think a bit, like do again the step back and look from last week, from 2 days ago, how neural networks are calculated, and then see why we might want to use them on GPUs. I hope by now this picture is like clear to you and you understand what is a typical feed-forward neural network. We have the different layers, and what we mainly do is like we always calculate the activations at each layer, which is the weighted sum of all its inputs. and then we do an activation function on it, and this is how things are shown typically. If you now look at the mass, what you really do is the following calculation. So we have some input that is given, we have some weights, that is a matrix in this case, so ij. The weights depend on the one hand on the input it is connected to, and on the output in the output it's connected to. And then in order to calculate one layer, we have to iterate over our output, then iterate over input. So we have two loops here. We just sum up the weights times the input, and at the end we apply our sigma. So this is how, at least I would assume, if you have to implement neural network on a normal CPU, this is how you would implement it, and then you would run it, and you would get correctly all the correct results. So everything is fine with this, as efficient as you can do it, and somehow the best we can first do. However, now if you think a bit back on like how things are implemented, now I guess it's a long time ago, in more basic computer science lectures on hardware, you have quite a lot of jumps here. So every loop you have to do jump, you do a comparison, and based on the comparison, you either jump into the loop or you jump out of the loop. So although all the computation is somehow clear up front, I mean, it's completely clear how you have to do the calculation. When you run the code, there's always like things that where you have if conditions, and so the calculation might be a bit slow. So the question is, can we not do things faster on the hardware and somehow implement it differently? And in order to do that, there's two things, or I should remind of. On the one hand, there is the vector representation. So instead of like representing it in this type of loop scenario, the other thing you can do is represent that just as a vector matrix multiplication. And then if you're doing that, there's another principle in parallel programming, same operation on different data, SIMD, I think it's called, and there is specific hardware for that to do it efficiently. And that is something which is typically in neural networks. I mean, otherwise it's not surprising. We have these small units, and we have a lot of them to do that, and they mainly all do the same thing. So maybe we can gain from that, and if we're doing that, and that's exactly the idea when using neural networks, that we try to benefit from that we mainly have to do similar or the same operations on a lot of different positions, and they can all be parallelized. So they normally don't depend on each other. Normally you have dependence assumptions, but the nice thing with this matrix multiplication, how you calculate the first node and how you calculate the second node is completely independent from each other. Of course not, and you go to the further layers, these calculations depend, but within one layer, you can parallelize the things. So instead of the previous formulation, what we can do is also, which we have here, we can, as we already mentioned last time, we can look at it as a matrix multiplication. So what we're doing in order to get our output is we take our weight matrix W, we take the weight matrix, multiply it with our input, which is a vector, then we are getting our hidden state, and there we have to apply our activation function. And again, the activation function has to be applied at each position independently. So it's again a very like fast and parallelizable operation where we can do this all in parallel, and we don't have really conditions on each other. So this somehow motivated on how should we do this type of calculation. And for a long time, the default thing is, of course, you can use a CPU, which where you have nowadays also quite a lot of different computational units. You can run several cores in parallel. However, they're normally optimized for really doing serial optimizations like jumps, you have the look aheads and so on. So you have increasingly more cores and you can parallelize more, but that's not really for what they are optimized. They're optimized for complex code where you have jumps in there and so on. In contrast, if we are looking at our metrics, our neural network implementation, what we are having here is we have typically a fixed sequence of operation that we always have to do in exactly the same way. There's no branching in there. There's no conditions on what we have to do. And several of these operations can be done in parallel. We don't have to like wait for other results, but we can do these operations in parallel. And of course, people first started to do like to parallelize these things on CPUs, and you can get very nice gains. However, there is one quite very different field where something similar like this is also necessary, where you have to do these types of matrix operations. And that's first a very different field. That's like where GPUs are used. So imagine you have this description of a scene, like this 3D surface, the material and so on. And now you want to calculate this type of image. That's where shaders and where GPUs are used typically. That's where they were invented for. I guess a lot of you were depending on that when playing video games. So this is where original GPUs are used for, where companies developed the specific operations for. The interesting thing is now that the type of operations you need here is also mainly matrix multiplication. So it's very similar to that. And that's why gave rise to the idea of can we use also GPUs to do that? And that is what we're currently doing. So what are GPUs? Again, this is not hardware lecture. You can learn a lot more details about GPU. I'm not the expert on telling you that. But for us, the more important thing is that, yeah, they have a lot more compute cores. So you can build these pipelines there, which do a lot of parallel operations. And then you get really, really high output. Of course, they got merged a bit more. Each of the operations can get more and more complex nowadays. We have more advanced GPUs. Of course, also the hardware developers at some point noticed that AI gets a very, very important use case for them. It's even nowadays they're framing partly as AI chips and no longer as GPU, as graphical units. And then, of course, you're developing them then to be even better for AI. But the main idea was at the beginning, okay, we can use these types of chips in order to do that. And that really speeds up how much calculation you can do. And that is one of the main drivers of improving like AI, because the very important, very nice thing of deep learning is you're just getting better with more data, which is somehow really nice. You don't have to put effort. You don't have to develop great ideas. Typically, you can improve your model by just keeping it run for more time or like more iterations. And if you have more processing, you're getting it even for free, because what took you 1 week before, now you maybe takes you only 1 day or like some hours. Normally, you're not then happy, but what you just do is you're waiting just for two weeks, and now you're running it for 2 weeks, but you're like having 10 times more data. You're not having 10 times as good performance, but maybe double as good performance or something like that. So that is like a major importance, as we already mentioned in the history of neural networks, when people started to use GPUs instead of running them on CPUs. Some ideas of how they are different. No worry, I will not ask you about how many cores there are, but just to see a bit the difference. So on a CPU, you might have, I mean, this is older things, you had 10 cores, but you had 10,000 cores in NVIDIA, but each of them, of course, is not as powerful. So you're restricted in what you can calculate. You can't do any type of calculation as you have on CPU. On a lot of things, they are very slow, but on things which are important for neural networks, these types of GPUs are very helpful if you write the code in the right way. And now you have even specific ones which are good for AI. There's even newer things like the TPUs, but I guess you can't use them. Normally, you can only use them if you're at Google. But in generally, there's dedicated hardware. And this, of course, influences also then, as I said, what you develop. Because if you know, oh, matrix multiplication is super easy, you maybe do more things where you do more matrix multiplication, but other things which depend on conditions, you're not preferring as much because you can't parallelize it. Well, for example, come to that, and that's why you should keep it in mind. There is different ways of how you can do neural networks for sequences. Typical things are RNNs or self-attention. And again, the self-attention, the big advantage is in training, you can parallelize it better. You can just do a lot more parallel operations. And that's one of the big advantages of doing that. Okay, so how does that now work? How can we use a GPU which was developed that you can somehow create graphics on that? How can you do that and use that for doing neural networks? And now we'll do like 3 slides of a bit of history, and then we'll see that nowadays it's a bit easier. The nice thing is, at least in the practicums here, you don't have to really worry about it. You have a higher abstraction level. But as I said, I think it's a good and important step to understand the basics below that in order to get. So originally you had these types of pipelines where it processes the information from the input we saw as what should be done in order then to generate the images. And then at some point there were like, you could put your own code into this pipeline in order, for example, to support different materials or different lighting conditions. So you could plug in your code into these 2 things, the fragment processing and the vertex processing, in order to, like, if you want to do something special about some elements. And what is then done is that the pipeline will put this calculation that you implement yourself at this position onto each pixel, and you can modify some code which does work on each pixel, and it's parallel processed on all of that. And again, here we are. Also in shading, what you have to do is mainly you have to apply the same processing on each part of the image that is in there. So early works of GPU did exactly try to do that. So the idea is, in order to use it for scientific computing, what you create is you take your image, which is just, for example, an output array, which has 512 times 512 things. And then you write your shader, which is mainly this type of computation. And then you can use a GPU to process it, because each image will be processed, each pixel will be processed in parallel. So if you write how to combine 2 inputs into 1 output, then you can write it there and do it. And then this gets all parallelized, and you have some work. The nice thing is now things get easier. You have the so-called general purpose GPUs, and there you can somehow add your code. And on this second part, we will look now a bit. So the idea is now in CUDA, which is like at least the most common thing to do that, is that if you have on the first hand, you have the host code. This is running on your CPU. And the CPU says at some point, oh, I need to do this matrix multiplication, and sends it to the GPU. So what you're doing is you're allocating then some data on your GPU. You're copying the data there. And then you have these device code, which should be run in parallel on all the elements of your matrix. And when the GPU tells that, then you tell the GPU to run this code, and when it's done, you have the results there. So the idea is you have dedicated what is referred to as kernels then, which you can run, and this will run like in parallel on all the different data units. And that, of course, makes things now faster. You think if you have matrices of like 1 million, no, 10,000 elements or so, so 1,000 times 1,000 or so. If you can parallelize things and these can be run in parallel, there's normally no like dependency on each other. That makes things fast. And this is how this works. We'll look today a bit how these kernels look like on very, very simple examples. So there's a lot of work on that, on making these things faster. Again, the nice thing is normally you don't have to work. You can just use the out-of-the-box kernels that are there, and they work decently good. But as I said, it's good to have a basic idea of how that works. Okay, and how that works, I guess the easiest or best thing to understand that is we'll do it on a very, very, very simple example. So just the adding of two matrices, where you hopefully then will see how things work in a GPU, and that things are a bit different than you would do it if you do it on a CPU or in normal code. So just imagine we want to just do the addition. So you have a matrix A, which is blue. You have a matrix B, which is purple, and then you want to get a matrix C, which is green here, and you have some fixed size. With matrix addition, of course, it's important that these have all exactly the same size. What is the mass definition of matrix addition? What do you have to do? Yeah?
The addition is component-wise, so you add each element at each index.
That's exact. So it's quite straightforward. If you want to calculate C at position I and J, what you have to do is you take A at the position J and I, and B at the position J and I, and you just add it up, and that's your thing. So this is the result, and that's what we want to do. And here you perfectly see how this can be super parallelized and how it might be good to run it on the GPU. So mainly you run now 12 times 6 different threads, which all do one of these calculations. And that is where the GPUs are then. I mean, there's, of course, now, if you think about it, I mean, we were most interested in matrix multiplication. There things already get a bit more complicated because you have to iterate over rows and over columns. You can look at that if you want and you're more interested in. Today, we will really look at the very simple examples of how you have to do that. And therefore, also, since this calculation is easy, the code that you run on your node is very simple. So as I said, you run a lot of code, like 12 times 6. So each code has like a thread ID, so an ID of which one it is. So of course it has to decide, well, what should I calculate? And the easiest thing is you calculate I and J based on the thread ID. So you have the size, then the J is thread ID divided by the size. J is thread ID modulo of the size. So then you know I and J. And since the ID is unique, each of them will get a different result here. Each of them will, like, it's not only unique, it's also like continuous. So you then have all of the JI examples that you want to have, and then it knows it, and you can just do your calculation there, and then you're done. So very simple thread, and then you would run this now 12 times 6 times, and these can all be run in parallel, and you don't have to wait for a for loop to go through all of them, but it can be all done in parallel. Things even get typically with newer GPUs more simple, because your thread ID is not one-dimensional, but n-dimensional. So you just do your I as your x-dimensional thread ID, your J as your y-dimensional thread ID, and then you're doing it there, and then you can run your code. Things get a bit more complicated again, because the threads are not independent from each other, but what you really have, you have a grid of blocks, and in each blocks, again, there's a grid of threads, so they're somehow grouped. So then you have to do again this type of calculation, which we had before. So what you're doing is you're looking again at in which block are you, and in which thread of this block are you, and that gives you your ID. So to get Y, you look at your block ID times the block dimension, and then plus your thread ID, because like, for example, for X, there's like, in each block there are 5 threads, and if I'm now in the second block and the first thread there, I'm like, my ID should be 6. I do the same thing for the Y, and then again I have my ID, and I can just do my calculation, and that's all I have to do. So this is mainly the code that I have to do for doing this type of calculation. You can also look at this code now on like in kernel code. This is an example. So as I said, this type of code that you run on the GPU is referred to as kernel. So you have here the kernel code, which gets, on the one hand, in this case, 3 different matrices. You have the matrix A and B, which are the input, and you have the output matrix C, which is the output. Then you calculate based on your block index and thread index, which element is the one you should care about. And if you have that, you just do your calculation and you're done. And this code can then just be run. So the only thing is now that you have to somehow tell the system how often should I run this. So this is everything which is really run on the GPU. What we now need to know is what is referred to as the host code. So the code that starts everything and where you can start these things. This is even, I would say, more straightforward. So what we are doing there is we know, okay, we have 12 X dimensions, and in Y we have 6 dimensions. So we call our kernel matrix add on with the parameters A, B, C. So with the matrix A, matrix B, and matrix C. And then we're just telling it that our X is 12 and our Y is 6. And then we can do all the calculation. Again, it's a bit now, you have this additional thing about blocks and threads per block. So for example, if you have 12 threads per block, you say there's 4 in the one dimension and 3 in the other, so 12 in total. So then you can calculate how many blocks you need based on the splitting this again. You do these things on the number of blocks and number of threads, and again, you can run your code. So this is then the host code that is run on the CPU, which will start all the jobs you have on the GPU to do that. Any more questions on doing this? Okay, I hope that doesn't mean I've lost you. I hope it doesn't mean it was straightforward. Now, of course, a lot of things can get there or have to be considered to make that efficient. We said here at the beginning, this data has to be copied on the GPU. And so the question is, which data do you put on the GPU, which did you merge to the CPU, and so on. We'll not cover these details here, so it should give you more idea. But of course, there's a lot of things that you should, like what do you put into your kernels? How much calculation in each kernel? How do you best split the work if it's maybe a bit depending? So there's a lot of things that you can optimize. There's very different kernels. There might be then for larger networks that you try to optimize and develop optimal kernels for your type of application. So there's a lot of things that you can do there based on the basic. But I think it's important to keep this in mind because it tells you a bit what type of architecture might be easy to calculate and what do you have to wait and so on. Also, like what things are getting complicated. You see, of course, it's not that it doesn't matter how much how big your embedding or your hidden size is. It's getting more complex, but it's easy. But at least you see that it's easy to parallelize. So if you have now up to like 10,000 threads or so that you can run, you see that you can do a lot of things in parallel and do them. Good. So what we now know is that, yeah, with this idea of single instruction and multiple data, we can perform the same operation on this X several times because we have the W there. and then we can be more efficient. Now the question is that all we can do, or do you have an idea, if you think about this, you can maybe do things even more efficient than always taking our x and multiplying this with W1, and then we're getting the results there. That's some concept which we maybe didn't have yet. If you have learned a bit about training, you have learned neural networks, you've heard about this concept already. Anybody know how you might make things even more efficient? So the one thing to parallelize was what we now did is mainly across the dimension of x. So if x is a vector, we don't have to like iterate through it, but we can calculate all the dimensions in parallel. Right, there will be something else which we can parallelize, yes?
Many inputs we can batch them together.
Yes, exactly. So that is batching, and that is also essential for good performance, but you should think about some things there, and that's what we want to do next. So the idea in batching is, yeah, we might have even more parallelizability if we're not putting one example to it, but n examples. So if you then do that, instead of the matrix vector multiplication you have there, what you're getting is a matrix multiplication. So instead of having one example, you put here 5, 10, or anything examples, you do the multiplication, and then you get here the output for all your examples. So the idea is, yeah, maybe you're faster if you're not doing one example, calculating the backpropagation, and then do the next example or so on. But since they are again independent of each other, what you do for the one example and what you do for the other example does not depend on each other. It's like they should at least be independent of each other. So you can do that in parallel, and that's why you do what is referred to as batching, and you do these things in parallel, and you can do one, two, or many at the same time. Of course, there is a trade-off. What could be a first problem if you start to do batching? So the nice thing is we should get faster. You know that we can now do things in parallel, but you should also see here directly what might be a challenge.
Now, we calculate the rates after every input, or after every x. We have to process everything with the same weights.
Yes. Oh, yeah. Then we're coming to that. So in training, that's an important step. In inference, that might be okay, but in training, you're right. If you do an update, we can't do that. That's a very important part. At the part we come after next. First, there's another challenge. Even if the weights are fixed, and then this is fine.
So you obviously need more memory.
That's exactly. So that's the first thing, which is typically limiting your batch size, is the memory. So you have to store more. Is you not only have to store your input, you also have to store your outputs. Then, if you're doing backpropagation, you have to store your gradients. So you just need more memory. Memory is normally a scarce resource, and so you have to be careful. So yeah, there is a trade-off on this side. So on the one hand, you want to have a large batch size to do fast calculation, but on the other hand, a large batch size means you need a large memory. You have limited one, so you have to find somehow what is the best one to do. So this is one thing you have to consider, and that's why maybe you're going back to batch size 1 or something like that, because you want to have the largest model which fits in you, and then you only can have like one batch in there. The second thing is what you refer to is especially during training. So we said during training, we do backpropagation, then we do an update. And now, of course, the second calculation depends on the first, because now we have different weights, and that ones we can't do. Luckily, there is some way around it, and that is it's even good to not do an update after each update, but like to average over like several updates, average them, and then only apply these updates. And that's what we're doing. And this is also referred to as batch size. So you have to be careful if you're talking about neural networks. It's not always clear what you refer to as a batch. So either the batch size can be how much you calculate in parallel, or the batch size can be after how many examples you update your weights. And these can, of course, be the same, but they don't have to be. You cannot update before, so the hardware batch size has to be smaller than your update batch size. But of course, you can aggregate over several iterations and then only update. So your update size can be larger than your hardware batch size. But they have the same name because initially they were often used very similarly, but since like there's hardware limitations and so on, now often this is not the same. So be careful to what things refer to. And inference things are also not as easy. So the nice thing is there we don't change our model. So there's no problem of doing that. But depending on your use case, you might not have all your data available. So if you think about like a large language model, like people typing in there, it's not that all type at the same time. So often you maybe only can, depending on your size, you can only process one by one. Maybe you are a big company, so you're not answering directly, but you get within 1 second enough requests. Then you can, of course, batch, collect them, and then process them. Also, like it might be cases if you're just processing a document where you have a lot of examples independent from each other, you can batch them and process. So also doing inference, batching is interesting, but it really depends there also on the use case. Sometimes you can do that, and sometimes you can't do that. And finally, there's another point, and that is that there's also model limitations. So in order to do this, batching, here it was, you see, you have to have exactly like the same type of architecture for all examples. For standard feed-forward neural networks, that is the case. There it's straightforward, everything is the same. But as you've seen in the outlook, we'll later talk about self-attention, about RNN, especially if you think about your architectures which can handle different input sizes. This is no longer the case. And then things might get more complicated because you cannot process. If you think about a text, it can be 5 words or 10 words. And how can you like put them there in parallel in there because you only have different sizes in there. But yeah, that is just to keep it in mind. And again, it's like affecting where the hardware and the model affect each other, and that you should keep that in mind. Good. Any more questions of how to do your GPUs? Or you're now ready to work for NVIDIA? Good. Then, of course, we're not at the end, but maybe we want to do more. Why do we want to do more? First of all, yeah, you see, you can improve really, really huge when you go from CPU here to GPU. So this is the calculation speed or like the time you need for calculating 16 forward and backward times. VGG are like the graphical networks, ResNet also, and now they're older, but you see, yeah, there's really like things get really fast when you can do that on a GPU. So this is good, but now you're there and you can scale up and you want to improve further. So the question is, how can you get even faster? Or another, faster always correlates well, you see here with price. So here it's gigaflops per dollar, and you nicely see that with CPUs, the price stayed similar. It was GPU price got cheaper, so you can do more calculation per dollar. But that may also means maybe, yeah, it's no longer enough to calculate just on one single GPU. But the question is, if we now have a single GPU, the problem is these models might no longer fit into a GPU. So the GPU gets somehow your limitation. If you have memory and you have that many parameters, you want to have now models which are bigger and which you cannot fit there anymore. Also, you want to train them, and so it's not fast enough. And so the question is, can we make things in parallel furthermore and use not one GPU, but use several? I guess you all heard if they're talking nowadays about, I don't know, Llama and GPT and Gemini and I don't know what. They'll tell you how many million GPU hours they spend. And they already see that it can't be on a single GPU because then we would wait for the next 1,000 years. So they are running this training on whole clusters where you parallel use a lot of the GPUs. And the question is, how can you do that? And there's different types of approaches how you could do that. And we want to at least get, again, only like a very like high level idea on all of these and how you can do them. So let's start with the first idea, and that is somehow quite straightforward, data parallel. The idea is, if my model fits on the GPU, I can use it on the GPU, but still I might want to be more efficient, which means especially in training, I'm not training on one GPU, but I split my data. That's why it's data parallel. Here's all my data. I split it, put it on several GPUs and train them. And then I can use all of them. And hopefully, if it would be perfect, things would be 3 times as fast. Of course, they are not 3 times as fast because there's one challenge that we have to do during training. Why do we need to do the aggregate and the distribute again? What do we need to aggregate and distribute? Train your model on GPU1 and you train your model on GPU2 and train your model on GPU3. Is it fine? Can you just use it and be happy? Or what problem might arise? Why do we need to aggregate and distribute things? Yes?
If you don't aggregate, then you would have just 3 independent models, but we want to update the weights about just one model.
Yes, exactly. So we would end up with 3 different models. It might be nice. I mean, all of them will not be much better than the one we trained only on GPU1. What we want to do is we want to have one model which would be at least similar to the one that is trained on one GPU. But you're not training it have to go through all data on one GPU, but you have to go through all of them. So what you do is you train on each them, for example, again for one batch. Then we need to aggregate. So we need to aggregate the changes that we're doing. If you remember, we have the weight updates that we're doing. So you have to now collect each of the model. What do the examples tell us? How do we have to change our weights? You aggregate them. Then you also have to tell all the models, oh, these are the new weights. These are the changes. And then you can run your next. So you see you're not 3 times as fast because you have to have your network or at least communication effort to aggregate and distribute again. Still, if you're doing it in a good way, hopefully you'll be significantly faster because this is done. And you see now already, it might be good if we have learning algorithms where we don't have to update after every 5 examples, but where we can average over a decent number so that you can do here quite a lot of computation. Then you do your update and then you just do it. The fewer updates you're doing here, the better it would be in the end. So the advantage is we can use parallel computation. It is faster. Of course, it comes with a cost. We saw that. Then we have additional computational overhead. So we can't, we have to distribute the updates again. And there's another challenge here. And the additional challenge is we can, of course, do that only if the model does fit on the GPU. If the models don't fit on the GPU, they're too big, then all that doesn't help us. So it only helps us for the scenario where you can fit one model still on a GPU. If it's too big, yeah, it wouldn't work. You can even extend that now to distributed data parallel, where the idea is exactly the same. The difference is before you assume that you have one, or you have several GPUs in one computer in one node. Now you can have just several GPU nodes to extend everything. You have multiple GPUs on multiple nodes, which is again nice. You have a lot more GPUs. So before, typically you might have 8 or so GPUs in a node. So the maximum you can do at 8. Now you have a lot of computers connected. Maybe they can all run in parallel. Of course, again, it comes at a cost. Communication within a node is faster than if you're going over network. So it just like increases the communication here, and therefore, of course, your gains in the end are a bit smaller. There is also, just from the idea, the so-called zero-power data parallelism, where the idea is we are not storing the full model on every GPU, but we're distributing the full model on all the GPUs, because of course for each calculation you don't need the full model. You always need only like some part of that, and then you always get only the data, the parameters that you need. That's why it's called zero-power data parallelism. So each model now has only like some part of the layer, and when a layer is processed, you distribute this part to the remaining GPUs. And so you can somehow, again, save more memory and have like bigger models on them. So here is a bit of a visualization. So imagine you have like here n GPUs, and the baseline model you store like everything you need. So what does it mean, what you need to store? You have the parameters, that's what we have before, that's in blue. You have your gradients, so how you update it, that you also have to store over time. And then we'll come to that. So now we had very simple optimizers which just aggregate. If you want to do state-of-the-art methods, your optimizer has to store more about it, like momentum, somebody mentioned last time, a lot more information. So all of them are stored now everywhere. And what you can now do in zero-shot data parallelism is that you're not storing everything, but you're only storing, for example, the parameters and the weights everywhere, and the optimizer states are distributed over all GPUs, or also the gradient, or also the parameters, which means that, yeah, you see that you need a lot of less memory. So while initially with n equals 64, so you have 64 GPUs, while you had 120 gigabytes, now you have only really like around 1.9, so like 1/64 of the memory. You have, of course, a lot more communication here, or some more communication, but you see that you can save memory, and that's meaning, oh, you can again use larger models with the same GPU. So it's more efficient in order to do that. Any questions on that? Good. So then, of course, there's the other way you can go with it. Instead of distributing the data, you can distribute the model. That's a bit already in here. So what you're doing is, if this is your model, so you have your input, you have a two-layer model, so the easiest one. So you split your model into two parts, where one part is lower and the other one is upper, and then the one part of the model is in GPU 0, and the second part is in GPU 1. Now you see, oh, this is nice. That means, oh, you can have your model in there and have your model in there. So now you can have double as big model and efficiently train them. As always, if something is nice, there's also a disadvantage. Do you have an idea what could be a disadvantage if you put, at least if you do a basic implementation, if you put your one model in GPU 0 and one part and the second part in GPU 1, and now you do your calculation? Yes?
they're dependent on each other, so the GPU 0 in this case has to wait on GPU 1.
Yes, exactly. So there's a lot of waiting in there. So if you have more parts and even 4 devices, this is how it looks like. So first device 0 will calculate the first part, then the next part will be calculated by device 1, by device 2, and device 3. So that is a forward pass. Then you have to do your backward path where you go the other way around. And okay, then the updates of the weights, that is good. They're independent of each other that you can do in parallel so that you can do at the end. Now you're all advanced computer science students, so you know that you can do better. What would you do? Yes?
Pipelining maybe?
Yes, exactly. So what you do instead is you split your calculation in some parts, in smaller batches, and then the first device 1 is calculating the first part, and then you give this part to device 1, and then device 0 during that time is doing the next thing. Then you further do it, so then all 3 here, all 4 are even processing. Of course, at some point, all your data is done, so then it goes up again. You have all your forwards, and then you do your backward pass. You do it again in parallel, and do your updates. So you see, there are still things where GPUs are not running, but in total, this is a lot less or a lot more efficient running than before. So you can do that. There's a bit of a challenge with that. You have to normally adapt your code to do that and to efficiently do that, which of course, again, might hinder this type of application because you cannot just like run your code on multiple GPUs and it's happy, but you have to consider how to parallelize things. But you see that this, of course, is more efficient and might be better in a way. Any more questions to that? Okay, so until now, there was no always looking at it from the full GPU, from the full model. So we split the full model or so. What you can also do, and what is even partly done, is more looking at the individual matrices and even distribute them. So even like that is what is called tensor parallel, is that even the calculation of a single matrix, you might distribute over several GPUs. So again, the idea is if you're doing your input and multiplying it with A, you get your Y. What you can do is you can distribute, for example, A on 3 GPUs, then you do X times A1 gives Y1, X times A2 gives Y2, and X times A3 gives Y3. And now you have these 3 results. So you have the same result, it's just still distributed on 3 different GPUs. And then, of course, you might do further processing, and we'll see one example where, for example, you can do that on an MLP, and again, you're distributing things, and you see again, now you only have to do 2 calculations. I mean, of course, you won't do 2, you'll do it on bigger ones. From the idea, you can do 2 calculations on that instead of 6 up there. One example where that, for example, is done is Megatron LM, where this is now done for a full feed-forward network with dropout. So we'll talk later about dropout layers. What dropout mainly means that during training, it might be advantage to like erase some of the neurons and ignore them. We'll later come why this is good. So you don't have to worry about what you're doing here. Is you have 2 calculations we see. So the first one is that you do Y is like some activation function here times X times A. So normal NLP. And then the second part is you have a second layer. So Y times B. So the output there. And then you have a dropout layer here. And the interesting thing is here you split it and you do the split differently in order to minimize the communication. So the first thing is here you're splitting your matrix A into vertical into A1 and A2. And what you then get is you have your X on both, and then you get your Y where you have your Y1 and YB, and that is your first result here. Then you have to do Y1 Here, the B, you split this time vertical, you do Y1, B1 and Y2, B2, then you have that, and then you have to do communication to merge them to get the final Y, then you do the dropout, and then you get your set on that. So here you split the B and the A in different dimensions, because here your input is already splitted, so you can't multiply it completely. And then, of course, you have some communication, but you have here two layers, and you only have to do once the communication effort. Again, you see that, yeah, you can try to like somehow optimize these things to minimize in total the number of communication that you need to do. Good. So this is a bit, I think, from mainly Hugging Face, an overview on what you should do in the different situations. So which situations can you have? So the first one is you have a single GPU. So what can you do? The nice thing is if the model fits on the single GPU, you're done. You can just do what you think is the best. Then the nice thing is you can even do things if the model doesn't fit on a GPU. The idea is you use mainly the zero, so this zero parallel algorithm which we had, but you cannot upload to other GPUs. We don't have another GPU, but you can upload to your CPU memory or to your RAM, where the idea is that it will, of course, make things slow, quite slow, but at least you can run it on a single GPU. You always have to load the parameters that you need at the moment and run them. Then there's a thing, single node, multiple GPUs. If the model fits on a single GPU, you can distribute a data parallel, or you can do again zero. If the model doesn't fit, you do either pipelining or tensor pipelining, or you do zero. And if you have multiple GPUs and multiple nodes, it's often good to do like a combination. To do that, either you do zero, but then you need, the nice thing is you don't need modification. If you do tensor parallel, data parallel, and parallel pipelining, you need to do modification, but that is normally like less communication and therefore also faster to do. So this is basics for calculating GPUs on neural networks on GPUs. Do you have any questions before we're going to the second part of the lecture? Good. So we saw that one important thing when you train a neural network is this type of backpropagation. We did like a simple example. We last time goes through like step by step how you can calculate the derivation, how you can implement your backpropagation to do that. So therefore, you can now think, okay, we're done, it's perfect. We just, every time we invent a new architecture, we also define how we, or implement how we do the backpropagation, and that will give us good results. However, there are quite some fixed rules. I mean, there is clear how to calculate the derivation. We don't have, normally we have a fixed number of types of operation. We have some activation function, we do weighted sum and things. So can't we do that better directly by a program instead of every time like re-implementing these things? And the idea is to do it in the reverse mode. So what you do is your forward calculation is you can describe as a computation graph. So how the forward calculation is done is a computation graph where there's always one operation that we are doing. So and there's always clear rules how you can build the backward thing. So if you just build the forward one, you store the intermediate result there, and then the backward pass can be done automatically based on the rules and the stored results, which is of course nice. Then you don't have to implement your backward path. What you only do is you build your computation graph in the forward pass, and then you just run it forward and backwards through it, and you don't have to implement yourself anymore how to do that. So what do we mean by that? So for example, this is the typical computation graph of a feed-forward neural network. what we have is we have x and y, then we multiply them, then we have x times y, so there's a multiplication node, then we have our activation node, and then we're done. So this is the thing of computation that you do in the past. And if you have that, it's also quite clear for each node how to calculate the backward path. So to go the backward path, so at the output, we have the gradient is 1. So then in order to calculate the next gradient, we take our gradient, we get us from the way back, which is 1. And then you remember that for the sigmoid function, the gradient was sigma k times 1 minus the sigma k. K we have stored there on the forward path, so you need to store your results. And then you can calculate easily here the gradient at that position. And then you want to have the gradients at x and y, and that's again the linear function. So the gradient for w is gradient of k times x, and the other one is gradient of k times w. So we can easily calculate these gradients, and you see that we don't really have to do this by hand, but with automatic derivation, what we are just doing is we're building our forward path. So you're writing your code here, which will build the graph automatically, and for the backward path, the only thing you have to do is we call o.backward, and all the calculations we did before, which you have to implement yourself, will be done automatically. So yeah, you can jump over that and don't have to always do this thing yourself. There's major two ways of how you build a graph. We'll first add the one which is called dynamic graphs, where that means during runtime, so during you run the code, this type of graph is built, and then it will be executed also, and that also means errors will occur at that time, which typically will make your type of debugging a lot easier because you directly see where things are happening. So let's see how you would build these types of graph. Again, on a concrete example. So what you see here is, so we have x and y are just random variables. We have our weights, and then we do like several iterations where we train our loss. And each time we do the forward, which does a matrix multiplication with x and m. Then we do clamp min 0. Does anybody remember this is an activation function? We had the activation function, which was 0 for the negative, and then linear, so that is exactly here. So we don't have a ReLU, this max function there. And then we have the matrix, we do a second layer matrix multiplication with W2. That means then we have our output, and then here we calculate our loss, which is we do the difference between the predicted thing, which we had as the previous one. We do take the square from it and sum that up, and then we have our forward, and then we iterate then over and over again. So how does it go? So we can now do this type of dynamic graph building here. So what you see is for each variable that you have, you create here an object. So we have in our case the input x, the two weight matrices W1 and W2, and we have the output y. Then we have the first calculation here is the prediction of the forward path of the model. So what it does is it takes x and w, does matrix multiplication. We get our value here. We do our activation function. We again do the matrix multiplication with the next w, and that will give us here our prediction. That is a graph for the forward path, and then we extend the graph for the backward path for the loss. So we do the minus with a reference. We do the exponential. We do the sum, and this is finally our loss we're having. And this is now the graph, how we're calculating it. And now the backward pass is quite easy. So we saw how to build the backward pass. The only thing we have to do now is like do here the backward and calculate the gradients with respect to W1 and W2. You saw in PyTorch, you put that here. For X and Y, we don't need our gradient, but here you say require gradients true and require gradients true. So we see that we will store our gradients here for W1 and W2, and we'll then automatically like sum these up while we calculate our gradients. And then the next time in the for loop, we delete our graph again, it's dynamic building, and it's rebuilding the graph over and over again. So thereby you now see how you can do the calculation. You don't have to calculate here, you have to explicitly say how you do your backward pass, but that can be automatically done by the rules of the computation graph, because for each node in the computation graph, you saw when you have here a power operation, it's clear what is a backward. If you have a minus, it's clear what is a backward. If you have a matrix multiplication, it's clear what is a backward, and so on. So this is a dynamic graph. There's also the possibility to do that all that in a static way, which means in this case you're not, as we saw, like while you run the code, you're not building the graph, but in contrast, what you're doing is once at the beginning you build your graph, and then during execution you just run your data through this graph back and forth. So you always put different inputs, run them through, and back propagate, which has, of course, an advantage. I think it's quite obvious. That might be faster. You'll not have to rebuild your graph always, but you do the same input. So you run your graph back and forth. However, it comes also with two typical disadvantages. So once debugging is a lot more difficult, it will say, oh, something doesn't work. But where exactly things didn't work is no longer as clear, because it's not while you execute this code, normally it crashes and then you know. So this debugging gets a lot more complicated. And there is the problem with dynamic data structures. So this is again, for normal MLP, this is fine. And that's why in initial frameworks, so when people started to have deep learning frameworks like the PyTorch here, people started to do it with static graphs. However, this gets complicated if your data is no variable. If you again think about audio or text input, it's not always the same. But now you need to create a graph for fixed input. So you cannot have sometimes a short sentence and a long sentence, because for the graph X and Y have fixed dimensions, so you cannot do that. And that's why then people looked a lot more into making these dynamic graphs, because then for each example, or at least each batch, they don't have to have the same size, but you can have different size batches if you always create and recreate your graph. Good. Any more questions on that? Good. So what you hopefully have learned today is a bit how to run a neural network on a GPU or on many GPUs. So we did both. We looked how to do it in matrix formulation, how to run it on a computer, and how to run it on multiple GPUs. And at the end, we looked how currently, typically it's done that you calculate your backward pass. You don't have to do it by hand as we've done last time, but this can be done automatically. And yes, so this is also how you'll do it on Tuesday, as you've seen. So next Tuesday, we'll have the first practical part where you will work with PyTorch here, I think, and do some small networks and trying them. And then next Thursday, you're free because it's a public holiday. And then the Tuesday afterwards, we will have another lecture and then starting to look into architectures. Yeah, thanks a lot, and then see you again on Tuesday.